of these sources was of the order of 10 to the 37 ergs per second, which is 10 orders of magnitude higher than the X-ray luminosity of the sun. 10 orders of magnitude higher. As I said earlier to you, the object couldn't be anything like the sun. Between 64 and 66, papers were published by Ed Salpeter and by Hayakawa and by Zeldovic, in which they mentioned the possibility that a supermassive black hole was accreting matter, not a binary system. We call that Bondi accretion. And that the gravitational potential energy converted to speed, kinetic energy, and that might actually produce the X-rays. In 1967, Slosky wrote a paper in which he tried to explain SCOX-1. So this paper was only about SCOX-1. And he said SCOX-1 is a binary system. There is a nuclear burning star, and there is a neutron star, and there is transfer of mass from the nuclear burning star to the neutron star, and there is a huge amount of gravitational potential energy converted to kinetic energy. When it hits the neutron star, it gets so hot you get X-rays. And that was exactly right. And I will quote from that historic paper. And the strange thing is, I read that paper at the time. We didn't pay much attention to it. But I quote from Slosky: "By all its characteristics, this model corresponds to a neutron star in a state of accretion. The natural and very efficient supply of gas for such an accretion is a stream of gas which flows from a secondary component of a closed binary system towards the primary component, which is a neutron star." I'll show you now a slide which is sort of the idea that he had. Okay, so the basic idea is here is a nuclear burning star and here is a neutron star. Forget for now this disk, that's not important for now. And these two stars are so close together that it is energetically more favorable for the matter to go to the neutron star than to stay here. And so as it starts falling and falling and falling and falling towards the neutron star, picks up speed and speed and speed, so gravitational potential energy is converted to kinetic energy, and that means heat, and if the temperature is high enough, then you get X-rays. Now you can see why comparing it with the sun is an absurdity. If you compare these sources with the sun, you're comparing apples and coconuts, because the sun is a single object. But here, you see, this is the sun, so to speak. Here, this is the object that radiates the optical light, and this is the neutron star from where the X-rays come. And that can therefore also, in a very natural way, explain this crazy ratio that I wrote on the blackboard. Yeah, you can make it lighter again. We don't need this slide anymore. In 1966, the group at NRL, Herb Friedman, published the first X-ray detection from a galaxy in the Virgo cluster, which is 60 million light years away from us. They suspected that it was M87 because that's the brightest galaxy in this cluster, and that's what later was called an AGN. Remember? The student remembered that, active galactic nucleus. And the luminosity was 10 to the 43 ergs per second, which is equivalent to 1 million bright X-ray sources in our own galaxy. The first X-ray observatory, Uhuru, was launched on December 12, 1970, off the coast of Kenya. It was on Independence Day, and the Swahili word for independence is Uhuru. It was an all-American science observatory, and Ricardo Giacconi was the PI. Uhuru had 2 collimators, 1/2 degree by 5 degrees, and 5 by 5 degrees. and it's rotated around once in 11 minutes. In 1971, they published a paper, Minoru Oda was first author, in which they said it is very probable that Cygnus X1 is a 73 millisecond pulsar. This was a courageous statement because the time resolution of Uhuru was 100 milliseconds. And if you want to claim that you see a periodicity of 73 milliseconds and your time resolution is 100 milliseconds, nature doesn't work that way. And so it's not surprising that the claim was wrong. But Ricardo told me later, and I believe him, that this result, even though it was not correct, accelerated the search for pulsars in Uhuru. And shortly after that, in May 1971, they found 4.8 second pulsations from a source, SENX3. However, there was no observational evidence that there was a binary system. And to make it worse, the 4.8 second pulsations were not constant. On day 1, they were different from day 2 and day 3. And that argues against the neutron star, because obviously neutron stars cannot possibly change their rotation period on such a short timescale. X-ray astronomy was flourishing and dominated all of astronomy. That is no exaggeration. I went to the library this morning and I picked a random APJ letters, Astrophysical Journal letters. I picked a random one from August 1971, and I want to show you the cover page. And I don't want you to read all those names because that's not my objection. Now, there's something with the light wrong because we can't see this anymore. Oh, this has to warm up. All right, then we let it warm up. I would like, it's getting better. Probably conversion from gravitational potential energy to kinetic energy. So yes, there are names here, people who are in the audience. There are people who were at MIT who are here. That's not why I'm showing this to you. I want you to see how X-ray astronomy took over the field of astronomy. Read the titles: X-ray observations of Virgo XR1, X-rays from the Magellanic Clouds, measurement of the location of the X-ray source Cygnus X1, X-ray source positions for Cygnus X1, Cygnus X2, and Cygnus X3, on the location of Cygnus X1, radio emission from X-ray sources, X-ray observations of GX17+2 from Uhuru, and then a search for deuterium on Venus. How bizarre. Chandra Sekhar, who was the editor, must have had a very weak moment. The breakthrough came from optical astronomers, 2 independent groups, Webster and Murdin and Tom Bolton. They observed the most likely optical identification of Cygnus X1, and they discovered that it was a binary system with an orbital period of 5.6 days. But in addition, they measured the Doppler shift of the star that they saw. These stars have spectra, and these spectra have absorption lines, dark lines in the spectrum. And when the star is in a binary system, if the star comes to you, the absorption lines are shifted towards the blue, we call that blue shift. If the star goes away from you, the absorption lines move to the red, we call that red shift. And those curves are called radial velocity curves. And they measured the radial velocity curve of the optical component of Cygnus X1, and they knew it was a binary. Once you have that radial velocity curve, you see immediately the period, And you also get information about the speed of the star, because it's Doppler shift after all, so you get information about the velocity. And if you know your high school physics and you add Kepler's laws, to make a long story short, you can then find a lower limit to the mass of the other source, which in this case would be the accretor, the X-ray source. And this mass that they found was larger than twice the mass of the sun. As you all know, a white dwarf cannot be more massive than 1.4 the mass of the sun. We believe that neutron stars can really not be much more massive than twice, maybe 2.5 times the mass of the sun, because then they become black holes. Webster and Murdin published their data on January 7, 1972. And I will quote from Tom Bolton's paper. The high energies of the X-rays imply that large accelerations are involved. Accelerations such as might be produced by the intense gravitational field of a collapsed object. The lower limits placed on the secondary mass are too high for a white dwarf and probably rule out a neutron star. This raises the distinct possibility that the secondary is a black hole. These guys discovered, number one, that these X-ray sources were X-ray binaries, and the very first one, that the accretor was a black hole. I'd like to show you the radial velocity curve because of its historic importance. It's a Doppler shift curve. If the source is coming to you, then you have the higher velocity of the lines, so you're here. If the source goes away from you, you're here. And of course, the time from here to here is exactly the orbital period, which is the 5.6 days. So with this data alone, and with a little bit more, you can get the lower limit of the mass of the accretor. And that's an incredible accomplishment. The popular press and even the professional literature almost never mentions this milestone discovery. They credit Uhuru with the discovery of the binary nature of X-ray sources, and most also credit Uhuru with the discovery of the black hole in Cygnus X1. Both is incorrect. Uhuru did not discover X-ray binaries, did not discover that the accretor in Cygnus X1 was a black hole. The reason why people have it wrong is that only a few weeks later, after the publication from Webster and Murdin, Uhuru group showed that Cenex 3 is a binary system, orbital period 2.1 days, 4.8 second pulsations, a rotating neutron star. The 4.8 seconds showed Doppler shift, 2.1 day Doppler shift. So the 4.8 second period was not constant. That's why a year earlier they were so surprised that the 4.8 seconds changed all the time. Well, that was the Doppler shift in orbit. And they even saw X-ray eclipses. That means that the neutron star was hiding behind the donor star, and then the X-rays are blocked out. And that was so overwhelming. That was everything that you could hope for, that I think that may be one of the reasons why many people think that Uhuru made all these discoveries. The paper, Cenex 3, was submitted 2 weeks after the Webster and Murdin paper had already appeared in print in Nature, but it was not even referenced in the Uhuru paper. And I think the reason is not that they purposely avoided it, but I think these guys were so busy and so excited about Cenex 3 that they hadn't even read Nature. That's my explanation. However, if they had referenced that paper of Webster and Murdin, history might have evolved differently. I would like to show you the pulsations of Senex 3, which are absolutely fantastic. So the separation between the peaks is the 4.8 seconds, which is the rotation of the neutron star. Don't pay attention to this shape, because that's the result of the collimation of Uhuru. And then I also want to show you the eclipses. When the neutron star hides behind the donor, you see that here. With a little bit of imagination, when there is data, then you see very dark lines here, and then all of a sudden, nothing, and then back again. And during that nothing, the star is hiding, the neutron star is hiding behind the donor. And the period between these troughs is 2.1 days, which was exactly the same period that they found from the Doppler shift of the rotating neutron star. When the optical identification of Senex 3 was found, the mass could be determined of the accretor, and it turned out to be a neutron star. That was obvious because of the 4.8 seconds. Cygnus X1 never had pulsations, because Cygnus X1 is a black hole, and a black hole has no surface, so you can't get pulsations. But if you see 4.8 second pulsations, you know it's a neutron star. So that was not a big surprise. In 1972, Uhuru paper, Gursky was first author, had conclusive evidence of extended emission from the Virgo cluster, the Coma cluster, and the Perseus cluster. This was hot gas that was trapped in the potential well of the cluster. And it was so hot that it emitted X-rays. And the mass of that hot gas, as the student remembered, was many times the mass of the galaxies, and that has consequences for cosmology. There have been several Uhuru catalogues. The last one was the 4U catalog in 1978. The two first authors were Bill Foreman and Christine Jones, and the catalog had 339 sources. And a typical error box for the source was 2/10 of a square degree. And I remember I was with Herb Gursky at a conference, and someone asked Herb, how come that the optical counterparts, optical lie outside the Uhuru error regions? And then Herb answers, that's because the area outside is way larger than the area inside. I want to show you the Uhuru catalog results. The fatter the dot, the stronger the source. Galactic coordinates, you see here. And if for those of you who are nearby, they can see here's CoX1. You will probably see Cygnus X1 right here, and Senex 3 is also marked, is here. If we compare the situation from 1962, from the early days, the early 60s, with the situation now, and I'm particularly thinking of the Chandra Observatory, then the sensitivity of detecting a source is now 10 million times higher than it was in the early days. 10 million. And the angular resolution is 1 billion times higher today than it was. I will show you here a nice slide that was given to me by Fred Baganov. This is 8 by 8 arc minutes made with Chandra Observatory. And you see here 1,000 X-ray sources. None of these sources could ever have been seen in the 60s, not only because of the sensitivity, but keep in mind that the resolution in the 60s was of the order of a square degree, and a square degree is 20 times larger than the size of this screen. So none of this, what you see here, could possibly ever have been seen. A thesis was written by Hirsch on the history of X-ray astronomy, and they listed the names of people who in that decade had more than 13 publications on X-ray astronomy. And I surely don't want you to read all the names, but since this is MIT, I underlined the people at MIT to show you that MIT was extremely active in the early days. So, Bill Smith, Gordon Garmire was at MIT, so he had 16 papers in that decade. Srikantan was at MIT. Sal Rappaport was at MIT. George Clark, with whom I worked. Hale Brott, sitting right here. Hale had 23 papers. Or did he have 22? Well, if he had 22, I had 23.